Okay, the question looks big, but the answer is simple. Let me read out the question and explain you. Consider n process sharing the CPU in round robin fashion, which means they are saying that we have n processes which are running in round robin. If the context switching time is s units, which means context switching time means when you are in one process and if you want to change it to the other process, the time taken between that is s units. What must be the time quantum q such that the number of context switches are reduced, but at the same time each process is guaranteed to get the turn at the CPU for every t seconds, which means they are giving you some parameters. One is the context switching time, and then the time quantum, and then the number of processes. Now they are asking you how much should be this time quantum adjusted so that every process will get its chance every t seconds, right? So in order to answer this, we can take simply a few number of, okay, the question is like this. If you are having n process, then if you are scheduling them like this, p1, p2, p3, so on, pn, and again p1, then between every two process, this time is called as context switching time. Why? Because you have to change the context from p1 to p2, from p2 to this one, right? So this time they are calling it as s seconds, and anyway this time is anyway equal to the quantum time, right, q. Now if this is the scenario, then if this thing, which means every process when it is executed next time, right, so that is what they are saying. See this, then what must be the time quantum such a way that the number of context switches are reduced, but at the same time each process is guaranteed to get the turn at the CPU for every t seconds, which means every process should get every t seconds. For every t seconds a process should get a chance to execute. Then how can we answer it is, before a process gets executed for the second time, how much is the time spent completely? That time has to be less than or equal to t, right? Then only the process will get the chance to execute every t seconds, which means once you start here and again you reach there, between this how much time is elapsed, and that time has to be less than or equal to t. So analyzing it with n process is a bit difficult. Maybe if you would analyze it, fine. Otherwise we can scale it down to 4 processes. Let us say I have 4 processes, p1, p2, p3, p4. Then again p1 will get scheduled, right? Then this is a context switch, context switch, context switch, and context switch. And now how many context switches are there before you get the same process? 1, 2, 3, 4. Therefore if I have n processes, I have n context switches. This is the time, plus before the same process gets executed, how many processes are getting the quantum time in the middle? 1, 2, 3, which means n minus 1. N minus 1 process will get a quantum time of q, right? So this entire time including the context switches and the execution time should be less than or equal to t. Then only a process will get executed 2 times within some time t, right? Okay, now what we should do is what is the relationship between this quantum time and the other factors. So I want to find out the relationship between quantum time and other factors. Q is less than or equal to t minus ns divided by n minus 1, where n is number of process, s is switching time, and t is the time for which every process will get a chance for the second time. Got it? So how did I solve it? Assuming that the same process has to be scheduled after some particular amount of time, I am going to think that the total time elapsed has to be less than or equal to t, right? Then you can see that before any process gets executed, there will be n time switching has to happen, and then n minus 1 process have to be executed in the middle if all the processes are available at the CPU, right? Depending on that, we got this equation. Got it? Very simple, but then you might have to think about it a bit. So whenever you are not able to get any answer for n process, you just scale it down to 2 process, 3 process, or 4 process, and then put back the solution in terms of n. That way it is very simple to analyze it. Okay, fine.